Electricity is extremely useful. It is the reason why I was able to make this video. It is the reason we are able to drive vehicles, use our cell phones to communicate, use a microwave or stove to cook our food without the use of wood fires. When talking about electricity, one is actually speaking about electric current. That's what electricity is. And we are going to be taking T-notes about this very subject. Let's begin. Electric current, denoted by the capital letter I, it is the movement of electric charge, which is carried by electrons. So if you remember that atoms have electrons, and these electrons have a charge that is negative, this is why we call this an electric charge, is because the charge is carried by electrons. Electric current is caused by energy that produces a potential difference. Potential difference just means that within the source where the energy is coming from, if that energy produces a higher or lower level of positive versus negative sides, then that would affect the electric current. When one end of the circuit has a higher potential, there will be a flow of electrons from the area of high potential to that of the low potential. In this case, from a negative to a positive. The direction that electrons flow is from a negative to the positive, so it would be in that direction. The electron source is actually the conducting material itself. Some people think that the electric outlets in their homes are the source of the electrons, and that is not correct. The actual electrons come not from the power plant, but from within the wire itself. So the electrons are within the wire and they are traveling through the wire. Here is a diagram of a battery that has been hooked up with a wire. A battery is a device that has stored chemical energy, and that is used to provide the force to move electrons. This battery produces a chemical energy that is transformed into electrical energy. If we connected the positive and negative sides of the battery, and this is the positive side, and here is the negative side, then the energy of the battery will excite the electrons inside the copper wire to actually move the electrons from the negative side to the positive side. This is what electric flow is. This is what electricity is. This is what powers everything that we use today. The electrons have a negative charge. The electrons would move from the negative end to the positive end. This flowing of electrons is called a current. What is an electric circuit? It's the circular motion of electric current that goes from the energy source to an object and then back to the energy source. One example is a battery to the light bulb back to the battery. For example, here we see the battery that is hooked up with a wire to the light bulb that is connected back to the battery here. So this is a complete loop. It is a circuit, and so the electrons are being excited by the battery, which is the energy source. It's exciting the electrons, and then it's pushing the electrons through the wire into the light bulb, and then the electrons go back to the battery. But remember that it travels from a negative to a positive side because there's that potential difference. This is an example of an electric circuit. Another example is the power plant that is connected to your TV, and the electrons would go from the power plant to your TV and back to the power plant. So the power plant is over here, and notice that there's all of these wires, if you've ever noticed, and they go through here and they finally get into your house, and then when the electrons are all excited throughout the wires, they go into your TV and your TV works, and then the electrons continue to travel back to the power source, which is the power plant. Here is an example of a simple electric circuit. We have the battery that is connected by wires to the lamp, which is connected to the switch, which is connected back to the battery. This is a complete circuit. If we were to look at this, this is what it would look like. However, In science and in class, we are going to be drawing something called a schematic diagram. And this is what it looks like. So we have these long lines here, which are the wires. We have this part here, which is denoted as the switch, and in this case, it looks like it has been turned off. If the switch were on, then this door would actually be closed, and you would then create a closed circuit. The light bulb is denoted by a circle with an X through it, and notice up here that the battery has two parallel lines. The short parallel line shows the negative side, and the longer parallel line shows the positive side. So you would know that it would be flowing from negative to positive, which would then be from the short side all the way across to the positive side. As long as this switch is turned on, the electrons can travel across and through the light bulb to the other side of the battery. When we're measuring current, we are actually determining the number of electrons that pass through a given point in 1 second. Current is measured in amperes, and amperes is denoted by the capital A. You've probably heard of amps. So 1 ampere or 1 amp is equivalent to 1 coulomb. This unit of charge, the coulomb, is 6.24 times 10 to the 18th electrons per second. So if I were to say 1 ampere, you would know that every second there is 6.24 times 10 to the 18 electrons that are being pushed through one point at any given time. Voltage and electrical resistance are two things that can affect electric current. The first thing, voltage, which is denoted as the capital V, is pretty much the difference in electrical potential between two different places in a circuit. It is the amount of force that pushes an electrical current, and its unit of measurement is also denoted by the same letter, V, which stands for volts. The voltmeter is a really useful tool in order to read the volts that is from a source of energy. Here's an example of a 9-volt battery, and this voltmeter has a red wire with an indicator here, and then a wire over here that is black, and the black side would touch the negative portion of the battery, and the red indicator would touch the positive side of the battery. And what would happen is the flow, you have a connection, you have created a circuit, and this circuit is going to go from the negative side through this voltmeter back into the battery over here. And because this is a 9-volt battery, we wanted to know what the difference in charge is between these 2 points, how strong is the source. So what we notice here is that it is 8.754, which is pretty close to the 9 volts that it is. This could mean that maybe the chemical energy that is inside of the battery is starting to wane. It is getting less. Also, you do have a little bit of resistance within this voltmeter. So what you have is you have a reading of 8.754. Here the voltmeter is hooked up to a US outlet, which should have a reading of 120 volts. We put the negative into the one part of the outlet and the positive indicator into the positive portion of the outlet, which then creates a perfect circuit. It's a closed circuit, so therefore the electrons will start to flow in from the negative, go into the voltmeter, and back to the power source. Here we have a reading of 119.6. Electrical resistance is a material's tendency to resist the flow of electrical charge. In other words, this pretty much just means it measures how difficult it is for current to flow through a material. This unit of measurement is denoted as omega, which is ohms. A resistor is anything that adds resistance to a circuit. It controls the flow of electricity. These can be objects that need electricity. They will have resistors in them. Some examples are appliances such as our TVs, stereos, toasters, ovens, and they can also be wires. Here are some examples of resistors. The electrons would go through this. The electrons, they would not be able to flow as quickly through these objects. And there are many different kinds that we use. Here we have 330 ohms, plus or minus 5%. So there's an area of uncertainty of how many electrons would be able to go through, what the resistance is. As you go further down, notice that there are different color bands here which denote how much resistance that resistor has. Here are some circuit boards that come from cell phones, computers, or any other electronic devices. And notice that some circuit boards have many different resistors in them. So there are many circuits that are on one board just for one electronic device. When you're looking at a schematic diagram, what you will notice is that here's the battery, here's the wire. If we have a resistor, it's shown as a squiggly line like this, and that just means that this is where electrons are going to run into some resistance. One exception to a device that does not have a resistor is the light bulb. And the reason why is because the light bulb itself is a resistor. One thing to note is as electrons move through the filament, so remember it goes from the negative portion to the positive side of the energy source. And what we have is as electrons are pushed through the light bulb, it goes into this part right here called the filament. And they bump into the metal atoms. And so what happens is the electrons are bumping. They're going through this filament. And because of the collisions, the filament lights up and heats up, and this is where we get our heat, and this is how we get the light. So notice this filament is super skinny because you're actually trying to create the space and the environment for the electrons to bump into each other so that it can glow. One factor that can affect resistance within wires is length. The longer the wire, the more resistance. For example, if you have this shorter wire and your electrons are trying to move through this distance, this length of wire, you will have a certain amount of chances to bump into the atoms of the metal or with each other. The longer that the distance is that you have to travel from start to finish, you have a higher likelihood of possibly bumping into other atoms. Remember that resistance occurs as the result of collisions between charge carriers, electrons, and the atoms of the wire. So if the wire is longer, there will be more chances of collisions. More collisions mean more resistance. Thickness is another factor that can affect resistance. Thicker wires means less resistance. If you have a larger cross-sectional area, for example, here is one wire that is smaller in section than this second wire down here. So if you have a larger cross-sectional area, you're going to have lower resistance because the electrons have a larger area that they can flow through. I always think of like cars on a highway. If you only have one road that all the cars have to go into, you're going to have a higher resistance versus if you have a wider road or multiple lanes for the same amount of cars, you're going to have less resistance. Temperature is a third factor that can affect resistance. The higher the temperature, the more resistance. Let's use our knowledge of how heat affects the motion of molecules. When a wire is cold, the particles such as the protons are not vibrating as much, so the electrons can run between them fairly rapidly. Here, the example of the protons being still because it's colder, and so the electrons can travel without having to hit them as much as if the temperature were warmer and everything's moving around. You would have a higher chance of the electrons bumping into these. Therefore, warmer wires means a higher resistance. conductivity of the material is the fourth and last factor that can affect resistance. This is caused by the structure of the atoms that make up the material itself that the electrons are traveling through. We know that all matter is made of atoms. Each material is composed of different atoms which have different numbers of subatomic particles, and we know those to be protons, neutrons, and electrons. Those particles are linked together in a specific way, and it gives each atom its unique chemical identity. The structure of each atom determines how easily the electrons can be removed from that atom. This ability of an atom's electrons to move is known as the electrical conductivity. Materials like metals have a high level of electron mobility, which means that it has a low resistance. The electrons can move around easily. If the electrons are not able to move around as easily, we tend to call these insulators. Here are some examples. At the top, what you'll notice here is that one of the best materials to use for electrical charge is silver. It has a very low resistance. And as you go further down from copper all the way down to glass and hard rubber, we have a high level of resistance. Because silver is very expensive, we tend to use copper, which is still pretty good and much more affordable. There is a relationship between current, voltage, and resistance, which is known as Ohm's law. This is that current is equal to the voltage divided by the resistance. Current is in measurement of amperes, and voltage is in volts, and resistance, denoted as the capital R, is in ohms. If you know any of these two factors, you can solve for the last variable. Here are our three equations if we were to solve for current, for voltage, and for resistance. And one of the things that I just wanted to show you was what the units of measurement would be for each. When you're solving for current, the units of measurement will be in volts per ohms, which we know is amps. When you're solving for voltage, and we have current times that of resistance, we have amperes times ohms, which we know that amps are volts divided by ohms. And the ohms would cross out, which would then leave you volts for your voltage. With resistance, we have volts divided by the current, which we know is V divided by ohms. The voltage would cross out, so the volts would cross out, and you would be left with ohms. This is just to give you an idea of how you get your units of measurement when you're solving for certain variables. Here's an example. A toy car with a resistance of 2 ohms is connected to a 3-volt battery. How much current flows through the car? We are going to use our equation, and we are trying to solve for current, which is I. When you plug everything in, you would get 3 volts over 2 ohms. You would get an answer of 1.5 amps, and if you were to take into account significant figures, your answer would actually be 2 amps. All right, we are done with our T-notes. I hope you understood everything and be ready to apply this in class.